Hello, welcome to this course in statistical physics. Today we're going to look at another way to derive the canonical ensemble probability distribution, and we'll do so using the Gibbs definition of entropy. In the last lecture we used the Boltzmann definition and it led to the canonical ensemble, but because the Gibbs and the Boltzmann definitions of entropy are completely equivalent, there should be a way to derive the canonical ensemble using this other definition of entropy. So remember, according to the Gibbs definition of entropy, the entropy of a system is equal to the minus Boltzmann constant times the average in the probability distribution we are considering of the log of the probability distribution we are considering. In other words, this is equal to minus kb sum over I of pi log pi. Okay, this is the Gibbs definition of entropy. Now, what is our goal? Our goal is we obviously want to maximize S. Maximizing the entropy gives us the equilibrium state, and it is how the ensembles in statistical physics are derived. But with the constraint that, first of all, the sum over pi's is equal to 1, so the distribution is normalized. This is quite obvious. But we also require that the average energy, right? The average energy, we require it to be constant. But essentially here we can get one Lagrange multiplier by noting that this value must be a constant, and similarly here we can get another Lagrange multiplier by noting that this value is also 0. Okay, so let's do this. Essentially, we want to maximize the following: S plus some multiplier alpha. Now I'll add the Boltzmann constant just for simplicity, times sum of pi minus 1. But then we have another Lagrange multiplier, alpha prime Boltzmann constant, times this. Okay, so we minimize it. What that means is we want to set its derivative with respect to pi. We want to set this derivative to be equal to 0. All right, so first of all, let's separately calculate this derivative right here, right? So what is the derivative of the entropy with respect to pi? This is a very simple calculation, and it leads to this. Okay, so already we can write minus kb ln of pi plus 1. Next, we can write plus alpha kb. Now, remember, this I right here is not the same as this I right here. So actually, if we want to be completely crystal clear, I should have used different subscripts. Okay, so we're taking derivative of some pj with respect to pi. Now, obviously, the only value that will survive out of taking the derivative of this sum will just be pi. So the derivative of pi with respect to pi, that gives me 1. And of course, this is a constant, its derivative is 0. And similarly, by the same logic, I get this is equal to just ej minus 0. And I set this equal to 0 to find the equilibrium, the stationary points. Okay, I factor out the kb, the Boltzmann constant, and I get minus log of pi minus 1 plus alpha prime ei. This should be an I. Yeah, equal to 0. Now, this minus 1 really doesn't matter too much, so I can just set this equal to alpha, redefine alpha to be this. And so I get log of pi, I move this to the other side, is equal to alpha plus alpha prime ei. In other words, pi is equal to the exponential of alpha plus alpha prime ei. So there you go, this is already starting to resemble the probability distribution of the canonical ensemble. We just have to figure out what these two values are. And we can do so by using the definition of temperature. As always, this is a very important definition. So recall that 1 over the temperature of the system is defined to be the derivative of the entropy of the system with respect to U. How does this help us? Well, let's try to find the entropy with this probability distribution. So the entropy will be equal to minus kb times times the sum of pi log pi. This is just a bit of algebra. So you will find that this is equal to alpha plus alpha prime ei pi. Okay, and well, this can be rewritten in the following way. This is equal to minus kb alpha times the sum over I pi, right, plus alpha prime sum over I of pi ei. Now, this should technically sum to 1, and this should technically sum to the average energy, which is also defined to be the internal energy, U. So all in all, this is equal to minus kb alpha plus alpha prime U. Wonderful. This is a very neat expression. We can put it directly into here, and we get that 1 over t is equal to minus kb alpha prime. In other words, alpha prime is equal to minus 1 over kbt, which we define to be minus beta. So we've gotten our first Lagrange multiplier. So we can write that pi is equal to exponential of alpha plus minus beta ei. Okay, minus beta ei. And this is really it. Why? Because now we just assume that the probability distribution has to be normalized. Okay, and to see this better, I can write this as e to the minus beta ei over e to the minus alpha. And then we clearly see that for this to be normalized, so for pi to be normalized, we need the sum over pi, right, which I can write as 1 over e minus alpha times the sum over I of e to the minus beta ei. I need this to be equal to 1. Rearrange this a little bit, and I find that e alpha is equal to sum over I of e to the minus beta ei. This, from our last video, remember, we defined this to be the partition function. So all in all, I find that alpha must be equal to log wait a second, e to the minus alpha. Oh yeah, sorry, this should be e to the minus alpha. That's right. Yeah, because I carried this over. Yeah. So e to the minus alpha. So this is equal to minus log of the partition function. Okay, we've determined all of our Lagrange multipliers. We're ready to write our final result. The probability distribution of the canonical ensemble is e to the minus beta ei times e to the divided by e to the minus alpha, so divided by the partition function. This is exactly what we got with the Boltzmann definition of entropy. And that's reassuring.